We are not done with problem 47 yet. I said earlier that you could get pretty far in this problem using Physics 161, length contraction and time dilation. I definitely do not recommend that you approach problems like this using just Physics 161, length contraction and time dilation, because it can land you in a big mess, um, because it can be really hard to understand what you're trying to do. However, once you already have everything solved using the Lorentz transformations, that will help you to check to make sure that you're using length contraction and time dilation correctly. So I think it's worthwhile now to go back and see how far we actually could have gone with this problem using length contraction and time dilation. I don't actually know that you'd want to fill out the whole table this way. I think in the end, to finish, I just ended up using Lorentz transformations. But we'll see how far we can get using length contraction and time dilation. So first of all, I'm just going to say for T2 and T3, in the Earth's frame, we just use Physics 161. So we still know that T2 is equal to 100 meters divided by c, which, if we need to know, is 3.36 times 10 to the negative 7 seconds. And T3 is 100 meters divided by 0.9 c, which is 3.706 times 10 to the negative 7 seconds. So then the next thing I want to figure out is, where am I when the light finishes the race? So we know speed is equal to distance over time. So distance is equal to speed times time. My speed is 0.9 c, and so where I am in Earth's reference frame when light finishes, so my position at T2 would be T2, which is 100 meters divided by c, times my speed, which is 0.9 c, which is 90 meters, which actually I had to figure out when I did the problem originally, because that gave me the 10 meters here, so I'm 10 meters. So the computer decided to stop recording in the middle of what I was doing, and I just noticed that. So we left off here. This was 90 meters, which we had seen was the answer. Well, that gave us the 10 meters for part C. So you're 10 meters behind the light when it crosses the finish line. And then we want the position of the light at T3. So we do speed times time. Now we're talking about the light. So the light's traveling at a speed c, and we multiply that by T3, and we get 111.11 meters for the position of the light when you finish the race. Now, the 90 meters and the 111.11 meters showed up in our calculation for T3 prime. And if you want to, I'll leave that as an exercise for you if you want to figure out why that is. I don't know if it is really anything profound, but you can think about that on your own if you want to. We're going to go in a different direction here. And we have event 2 in Earth's reference frame. Event 2 is when the light crosses the finish line. So the light's at 100 meters, you're at 90 meters, and you are 10 meters behind the light. Remember, as long as you stick in one reference frame, you can use Physics 161. In Earth's reference frame at event 3, you are here at 100 meters, the light is at 111.11 meters, so the light is 11.11 meters ahead of you in Earth's reference frame. Now, the reason that it's very easy to go astray when doing length contraction and time dilation instead of the Lorentz transformations is because of the relativity of simultaneity. So events which are simultaneous in one reference frame are not necessarily simultaneous in another reference frame. So I just introduced two new events. So that would be the light passing, here, the light passing the 111.11 meter mark and you passing the 90 meter mark. These two events are simultaneous in the Earth's reference frame, and these two events are simultaneous in the Earth's reference frame also. They are not necessarily simultaneous in my reference frame, and I'm going to show you now that they are not simultaneous in my reference frame. So this is what you have to understand if you're going to do length contraction and time dilation. Don't go assuming that these two positions for you and the light happen at the same time in your reference frame. That's where the trouble happens. Okay, so now we're going to look at the situation in my reference frame. So in my reference frame, we have a 100-meter long track. So that's the rest length of the track. It's length contracted when I'm running, and I'm running at a speed of 0.9 C. Oh, we already figured out that would give me gamma is 2.294. So in my reference frame, the track is going to be 2.29. I'm sorry. We're going to take the 100 meters and divide it by 2.294, and that will give us the length of the track is 43.6 meters. So now, when you start running, you don't see the distance between the start line and the finish line as being 100 meters. You see the track moving and thus having a shorter length. So when you are at the finish line, the starting line would be 43.6 meters away. Now, you cannot take this 100 or this 11.11 meters and divide it by gamma to find the position of the light when you cross the finish line, because these two events are not simultaneous in your reference frame. You could use that to find where the 111.11 meter mark is, but the light is not there in your reference frame when you cross the finish line. What we can do is consider you starting the race and you finishing the race. In your reference frame, those two events take place right where you are, which means the two events occur in the same place, so you measure the proper time. So now we're going to say delta T naught is the proper time, and that you started the race at 0 seconds, you finished the race at 3.706 times 10 to the negative 7 seconds. So the proper time from this is when you finish minus when you start. That would be, wait a minute. The proper time is measured in your reference frame. So this is the not proper time. So to find the proper time, delta naught, what did I say? To find the proper time, delta T naught, you would take delta T and divide it by gamma. So delta T, the not proper time, is measured in the Earth's frame. So that's the 3.706 times 10 to the negative 7th seconds. And you divide that by 2.294. And do I want to do it that way? Or do I want to do it with 100 divided by 0.9 divided by 2.294? I think we'll just go ahead and do it in seconds. So this gives me the time when you finish in your reference frame is 1.617 times 10 to the negative 7th seconds. So we, okay. Ignoring, oh no, this isn't exactly true. Let me do this again. 3.706 divided times 10 to the negative 7th divided by 2.294 gives me 1.6155. So if I write it like that, 55, well, that's closer to what I have in the table there. Okay, so it's just off a little because of rounding. So this was something to put into our table. So this I should know is 0 because, well, in order to say that this was the proper time, we said both events happen at the same place in my reference frame. So when I reach the finish line, my position in my reference frame is 0. So we got all of this just using length contraction and time dilation, but we had to think very, very hard. So that leaves us with when the light reaches the finish line in my frame. Now, at this point, I would just throw in the towel and use Lorentz transformations, because in the light's reference frame, you can't use the proper time because those two events don't happen at the same place for you. So the light is ahead of you by 22.94 meters in your reference frame when the light crosses the finish line. Furthermore, you don't know where you are when the light, no, you do. I mean, if you know this is 22.94 meters, you know where you are relative to the light, but we haven't found that yet. But you know you're not at 90 meters in Earth's reference frame. I mean, you know you're not here when the light crosses the finish line, because these two events are not simultaneous in your reference frame. So I would use Lorentz transformation still to find these coordinates, because I think we're kind of stuck because we don't have a reference frame in which event 1 and event 2 happen at the same place. I guess we could use the light's reference frame, but I don't think that would be helpful for us. But let's think about what this would actually look like given the results that we have here. So the light is 22.94 meters ahead of you. Or maybe we could do this. So you know this time. So, oh wait. Well, let's try it and see. Okay, so what is this time when the light reaches the finish line? When that much time has passed, I don't know what this is going to mean, but we'll just do it and we see what we get. When this much time has passed in Earth's reference frame, you are at 90 meters in Earth's reference frame, so I think that would just give you the time in your reference frame when you are at 90 meters, which should not be the 7.652 times 10 to the negative 8th. Let's just do it and make sure that is the correct way to think about it. So if I take this time and divide it by 2.294, that gives me 145.4 times 10 to the negative 9th, otherwise known as 1.45 times 10 to the negative 7th. 1.45 times 10 to the negative 7th seconds. So this is time in your frame, or I guess it was my frame, when you are at 90 meters, which is clearly not 7.652 times 10 to the negative 8. So this is why it's easy to fall into trouble here, because this is not the time that we should be using for event 2. This is not event 2. This is a different event. This is the when you cross the 90 meter mark, which is no longer in your reference frame simultaneous with when the light crosses the finish line. So where are you when light crosses the finish line? So this is the starting line. This is the finish line. When the light is at the finish line, you are 22.94 meters behind the light, but we had to find that using the Lorentz transformations. So you are 22.94 meters away. So if the track is 43.6 meters long because it's contracted in your frame, then you are 20.66 meters in your frame from the finish line. I don't know where that would put you if you're looking at the meter marks on the track, because they're closer together than a meter. But if you are using a meter stick in your reference frame, you would say you're 20.66 meters from the starting line. I guess we could go the other way around and we could say, if it's 20.66 meters in your reference frame, where do you see yourself on the track? So remember, the meter lines on the track are not really a meter apart in your reference frame. They'd be closer together because you have 100 meters on the track, which contracted to 43.6 meters. So the track is moving this way at 0.9 C. So what does 20.66 meters in your reference frame correspond to in Earth's reference frame? Maybe we could just do it this way. If you divide 20.66 by 43.6, you have traveled 47% of the way to the finish line. So since it was 100 meters, I think you would be at the 47.3 meter mark in Earth's frame. But these events are simultaneous in your frame, but they're not simultaneous in the Earth's frame, because when in Earth's frame, when light passes, you are at 90 meters, not at 47.3 meters. Okay, so then just to finish, I want to take 20.66 and multiply it by gamma, and that gives me 47.39. Oh, actually, that is kind of what I had. It is what I had. When I did this, I just didn't, I ignored the 9. It should have rounded up to 47.4. Okay, so this is where you are. This is if there was a line on the track at 47.39 meters before you started running. You are at that line when you see the light cross the finish line. But in Earth's reference frame, when light crosses the finish line, you would be at the 90 meter mark. I hope that didn't confuse you more. If you don't, let's see, you should understand everything that we did here when we solved problem 47. And this should just help you understand what is going on. But you don't have to feel like if you were completely lost when I was doing this, that's okay. You can think about it to try and help you make sense of problem 47, but you definitely don't have to know how to reproduce something like this for an exam problem or for a homework problem. Just stick to the Lorentz transformations, but this should hopefully help explain to you what's actually happening in the different reference frames and why we want to stick with the Lorentz transformations instead of trusting ourselves to length contraction and time dilation. But I think it is interesting after solving the problem to go back and try and figure out what is really happening.